Right, hello, I'm Ben, and today I'll be teaching you about the fascinating topic of string matching using finite state machines. It's basically a couple of algorithms that create finite state machines unique to the string that you'd like to match, and use it to try and find the string in another body of text. And because finite state machines support regular expressions, strings satisfying the regular expressions can also be searched for using this method. This can be useful for search engines like Google and other applications such as autocorrect software. Okay, so the easiest way to explain this is to run through an example manually before showing any code. Imagine we have alphabet ABC and we want to find the string ABABC. To find this string, we need length plus 1 states to allow for the 5 transitions ABABC. State 5 is the accepting state in this case. Now we have to fill in the transitions of the other letters in the alphabet. For state 0, only A can advance, so both B and C loop back round to state 0. For state 1, A can't move forward to state 2, but can loop back round to state 1 because it can be the start of another potentially matching string. C moves back to state 0. For state 2, neither B or C can be the beginning of another potentially matching string, so they both move back to state 0. For state 3, C moves back to state 0 as always, but A can move back to state 1. And for state 4, B moves back to state 0, but A can be matched as far as ABA, so it moves back to state 3. So now we have our completed transition diagram, apart from transition from state 5 because I've run out of space, but input A would move back to state 1 and inputs B and C would move back to state 0. I'll show you how it can be used to match a string in a minute, but first let's have a look at the algorithm that computes the transition function of this finite state machine. Here it is. It takes the string and the alphabet as inputs and gives the transition function as output. First, the number of states is calculated using the length of the input string. Then for each state, each character in the alphabet is analysed for where its transition should point. It does this by adding the character onto where the string would be if it were at that state, and then comparing it to the accepted string. If a match is not found, the leftmost character is removed and the string is compared again until a match is found. For example, at state 3, the pattern would be ABA and K would initially be 4. If a B was then input, it would be added to ABA to make ABAB. This would be part of the string ABABC, so the transition would be to state 4. However, if A was input at state 3, ABAA is not part of ABABC. K would then become 3, and the first A would be knocked off the string ABAA, making BAA. But BAA is not part of ABABC either, so K becomes 2 and PK becomes AA. Same goes for AA, so K becomes 1 and PK becomes A. Now the string PK is part of ABABC, so the transition goes to state 1. The same process would happen if C was input, but no match would be found, meaning its transition goes all the way back to state 0. Once the algorithm is complete, all possible state transitions have been worked out. Let's have a look at the time complexity of this algorithm. The first loop is order m. The second loop looks at each character in the alphabet, so it's order sigma. The first condition in the third loop is order k, which is order m. And with the string comparison condition, the number of individual character comparisons is at most the length of the string, which means it's order m as well. The rest of the code is order 1, which makes the complexity of this algorithm m cubed sigma, which is quite slow. Right, now our transition function is worked out, we could go on to actually matching the string with some other text. This is pretty easy to do manually, but there's an algorithm that finds matches as well. Here is that algorithm. First, the length of input string t is taken, and the state machine initializes at state 0. Then, every character in the string is added to the machine in order, and the machine progresses using the earlier calculated transition function. If the accepting state is reached, this indicates that a match has been found. The user is alerted of this, and the machine carries on to see if there are any more matches. Here is the algorithm at work, using our example machine and this input string t. The time complexity of this algorithm is simple to work out. Because there's only one loop, the complexity is just n. This gives the total running time of both algorithms to be n plus m cubed sigma. And there you have it, string matching using finite state machines. I only have one more example to show you, and that's using this technique to find strings defined by regular expressions in other strings. It's pretty simple. Just construct the finite state machine of your regular expression and compare it to the other string using the matching algorithm used before. For example, for the alphabet ABC and the regular expression C A star B, the finite state machine will look like this. Strings such as CB, CAB and CAAAB will be matched. Strings such as CA, AB and AAAAA will not be matched. This technique is used in software that suggests a similar but not exact string match. For example, the Did You Mean feature of Google Search and autocorrect software on smartphones. So there you are.